RAG retrieval breaks when top K is too small to find evidence or too large to stay focused. Use precision and recall in Python to tune it deliberately. This is the setup you'll be able to run after this, which compares retrieval K sizes and reports precision recall trade-offs. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Retrieval-augmented generation works like a librarian feeding context to a language model. You ask a question, the retriever brings back candidate passages, and the generator uses them. Pull back too few passages, and you miss the evidence. Pull back too many, and the model gets lost in noise. That tension is exactly precision versus recall. Precision tells you how many returned passages are useful. Recall tells you how many useful passages you actually found. Tuning that trade-off matters for FAQ bots, assistants, and any knowledge-grounded reply. Picture one question and a small document catalog. Your top list should include every doc that answers the question, while excluding the unrelated junk. Precision keeps the context tight. Recall keeps the answer complete. The goal is to measure both and pick a depth that suits your latency and safety constraints. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, we will start simple with a toy corpus and a lexical scoring function so you can see the trade-off concretely. This snippet seeds a tiny corpus and scores a query by lexical overlap. The list docs pairs short IDs with concise descriptions, while the dictionary doc sets caches each text's tokens so we avoid recomputation later. Inside rank by overlap, the query is split into terms. We count the set intersections against every document, sort the resulting tuples by score, and respect the desired K depth. Running the function on a precision recall themed query yields a simple print that confirms which document currently leads the ranking and how many shared terms support it. The snippet shows the core retrieval loop you will tune. The overlap ranking is useful, but we need to check whether the top results actually contain evidence. Let's compute precision and recall for a fixed K to see one snapshot. This example turns the top two overlap retrieval into concrete precision and recall numbers. We reuse the earlier query and extend the relevant dictionary so each question maps to the IDs that truly hold evidence. Rank by overlap returns the current top K list. We turn it into retrieved IDs, intersect with the ground truth set, and derive precision and recall ratios. Because larger K values would invite more context and potentially more false positives, the printed metrics expose whether this cutoff stays focused enough. The example uses K equals 2 as a visible example, and you can see how including an extra document lowers precision or raises recall. A single case snapshot is helpful but noisy. We need aggregated metrics across several queries, so trends become obvious. This snippet streams scikit-learn precision and recall calculations across every tracked query. Y true and Y pred gather Boolean flags per document as the loop walks the relevant dictionary, marking which IDs contain evidence versus which IDs rank by overlap surfaced. Precision score and recall score from scikit-learn convert those running flags into aggregate metrics without extra normalization work. Since changing the hidden cutoff inside rank by overlap would reshape both flag lists before they reach the scorer, the printed numbers reveal how retrieval quality accumulates across the evaluation set. This step turns per query judgments into dataset-level signals you can plot or compare. Now we sweep the top K parameter to visualize the whole precision versus recall curve, not just single points. This snippet sweeps top K values to map out precision and recall trends. Total_rel captures how many relevant items exist overall. Max docs preserves the catalog size. And the loop accumulates hits from rank by overlap for each proposed cutoff, because each query always returns min k max docs candidates. We can compute retrieve totals cheaply and append rounded metrics into the sweep list. Smaller k keeps precision high, while larger k pushes recall toward 1. And the printed tuples let you compare those trade-offs at a glance. The output gives a simple table of k, precision, and recall, so you can make an informed choice. Finally, pick the best k from the sweep and inspect the actual evidence the retriever would return for a key query. This example picks the best performing k and inspects the retrieved evidence list. The max function filters the sweep tuples by multiplying precision and recall, which favors balanced trade-offs without inventing a new metric object. Using the chosen depth, rank by overlap fetches the final doc IDs for the primary query, and summary packages the human-friendly numbers. The printed dictionary confirms the selected cutoff, along with the surviving evidence, so you know exactly what the tuned retriever would feed downstream. This final check ties numeric tuning back to the human-readable passages you will pass into a generator. Mapping this toy example to a real system is straightforward. Swap lexical overlap for vector similarity or BM25, and replace the tiny catalog with your document store. Keep the same sweep and selection logic, so you tune K against precision and recall on a labeled dev set. Recap. You now have a compact measurement loop that compares retrieved items to known evidence, so you can choose a cutoff that balances accuracy against context cost. Use this when tuning RAG to match your app's needs. One caveat: the best K depends on your corpus and label quality, so always validate on realistic queries. Next step, sweep the retrieval algorithm itself by swapping lexical overlap for vector similarity, and tune the same K on that index. That will tell you whether a different feature space gives a better precision recall frontier. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.